JewelsFallon will be our next presenter. Jewels is a fifth-year chemistry PhD student, and she knew she wanted to study chemistry when she realized she has no ability to sit still and loved being active in the lab all day. Her presentation title is Methods Matter, a new technique to make solid materials.
Most of us would probably prefer a diamond ring over a graphite pencil, but both diamond and graphite are made of the same thing, carbon. How we make things is just as important as what we make them from. This is true for pretty much all solid-state materials. Solid-state materials allow us to charge our phones, harvest energy from the sun, and go to all of our Zoom meetings. So in order to advance these technologies, we need to improve our abilities to make new solid-state materials. One big challenge preventing us from moving forward is the limited number of techniques we have to make these materials. Imagine taking two chunks of metal, like iron and selenium, and trying to get them to combine to form a new material. Bashing them together is just going to tire you out, because solid materials by nature are not very reactive, unless under extreme temperatures. For iron and selenium, you would need a specialized furnace capable of 2,000 degrees Fahrenheit, which is literally the temperature of lava. Even once you achieve this temperature, simply pulling the mixture out of the furnace to cool would cause it to cool too quickly, producing a useless blob, similar to our metaphorical graphite. Instead, to produce the diamond that we want, we must cool iron selenide slowly in the furnace over the course of 4 days. Like iron selenide and diamonds, many materials can only be made through a complex reaction scheme. This is where my research comes in. My research focuses on using an organic compound acting as sort of a molecular mixer to enable reactivity at lower temperatures, thus reducing the number of steps necessary to form that metaphorical diamond. So instead of taking my starting materials and heating them up to extreme temperatures, I take my starting materials along with an organic compound and heat them up to much lower temperatures, around what your standard kitchen oven can reach. Once the reaction is completed, it's easy to remove that organic compound, leaving me with my desired material. So in the case of iron selenide, I found that the key to low temperature reactivity was the organic compound interacting with the selenium. This simplified the preparation of iron selenide from a multi-step 12-day process to a single-step 5-day reaction. From this, I was able to expand to other systems, showing that this reaction scheme is broadly applicable. Additionally, I demonstrated that changing the organic compound changes which material forms, which introduces tunability into solid-state reactions. This provides solid-state chemists a new tool that can simplify the preparation of many materials and potentially enable the discovery of new materials that were previously unable to be made. This opens the door to new materials with widespread applications, such as batteries with longer lifetimes, more efficient solar cells, or other metaphorical diamonds we have yet to even think of. Thank you.